Hi everyone, my name is Kunal Minda and I'll be talking to you about structured mechanical models for robot learning and control. So we're interested in learning models of dynamical systems because we want robots to be able to act autonomously. And in order to do that, they need models that are able to predict whether an action that they take is going to lead them to favorable or unfavorable outcomes. Two real-world applications of this sort of model predictive control are autonomous driving and, as we've seen, SpaceX's ability to land their own rockets. So when learning a model of a dynamical system, one must choose a model class. The typical approach is to derive these models from first principles. And these sorts of models typically have free parameters, such as the mass of the system, that one would calibrate using some data gathered from the system. While we don't need all that much data in order to calibrate these systems, they typically suffer from model bias, meaning that there are certain phenomena that might be present in the real world that these models are not able to capture, such as joint friction. Another more recently popular approach is to use black box neural networks. So here we take the states of the system as well as the control inputs and pass them through a neural network that is to predict the accelerations on the system. While this approach is able to capture arbitrary phenomena that might be present in the training data, we typically require a lot of training data in order to generalize well. So these models suffer from model variance. So the question we ask is, can we get both the data efficiency of first principle models as well as the flexibility of neural networks? And we study a model class that we call structured mechanical models. The key insight here is that all mechanical systems obey Lagrangian mechanics. That is to say that if you were able to characterize the potential energy of the system, its kinetic energy, as well as the forces that were acting on it, then you could relate these terms through the Euler-Lagrange equation in order to get the system's equations of motion. So what we do is, instead of using a neural network to directly predict accelerations, we use neural networks to predict the terms of the Euler-Lagrange equation. That is, we predict the system's mass matrix for its kinetic energy, we predict its potential energy, as well as the forces that act on it. And we derive the equations of motion through the Euler-Lagrange equation. So in experimental validation, we compare the structured mechanical model, and we restrict our attention to control affine systems, hence SMMCs. And we compare this to black box neural networks in terms of their ability to generalize from limited data, as well as their ability to be used in optimal control. So in terms of data efficiency, we find on a multitude of robotic domains that for the same amount of training data, a structured mechanical model has orders of magnitude better validation error. When we use two models that have the same validation error on an optimal control task, we find that structured mechanical models are able to faithfully solve the optimal control task, whereas black box neural networks are not able to do so. And we show that the reason for this is that even though these two systems are able to get the same validation errors, structured mechanical models give more accurate predictions of the Jacobians. The one sentence takeaway here is that the variance of neural networks can be greatly mitigated by enforcing appropriate priors. We study mechanical systems, and so the appropriate prior to use is Lagrangian mechanics. Thank you for your time, and we look forward to your discussion.